When we say electrolyte, another common name you will see is as salt. The most famous electrolyte is sodium chloride solid. Once you put it into water, it's going to become sodium plus chloride minus in the aqueous solution. From the stoichiometry coefficients, you know if there's actually 1 mole of sodium chloride salt was thrown into your water, then it's going to produce 1 mole of sodium plus and 1 mole of chloride minus. So here we will use a term called the mu plus, where the mu is stoichiometry coefficient of the reaction. And then the plus just means Ki. And then the mu minus is actually the coefficient for my anions. Then the mu of my reaction will equal to your mu plus your mu minus. In this case, it's 1 plus 1, which is going to equal to 2. So if today you have another salt, for example, you have sodium sulfate, then you're going to have 2 mole of sodium plus 1 mole of SO42 minus. So in this case, your mu plus is equals to your mu minus equals to 1. Your mu reaction is going to equal to your mu plus your mu minus is equals to 2 plus 1 equals to 3. Another important term that we need to introduce is called the Z. Z is actually the charge of your cation and anions. So here, your Z plus is equal to 1 because your sodium carries +1 charge. Your Z minus is equal to 2 for your sulfate anions. Once you dissolve the salt into your solution, even though today you only throw 1 mole of sodium chloride into your solution, your sodium chloride is your solute. But the solute molecules inside your solution will be including sodium plus and chloride minus. In other words, if you want to know the concentration of your solute molecule, it will equal to a concentration of your original solute multiplied your mu. So this will equal to your mu times the original concentration of your sodium chloride. So the concentration of your solute molecule will be actually the effective concentration you should use for your calculation. Another thing that you should know is that sodium chloride, sodium sulfate, this is so-called a strong electrolyte. Once it dissolves 100%. But there are also some weak electrolytes. That means they're not going to dissociate 100%. Assume they actually only dissociate to alpha percent. Assuming today you know your original solute concentration is M. To calculate your concentration of your solute molecule, it's going to equals to M times 1 minus alpha. It's actually the not dissociate species. And then the part of that got dissociate is actually that much. And the dissociate one, you consider your mu. If you put these things together, then it will become M minus alpha M plus alpha M times your mu. If you pull out all the M, they will become 1 plus alpha minus 1 times your mu. So that will be actually your solute molecule concentration. And then for the ideal solution, that's actually pretty much all the things you need to know. When we head into the non-ideal solution, the only difference is that for the solute concentration calculation part is still the same. But when you calculate your mu, that part will become different. When you have a non-ideal solution, the mu you calculate is actually need to actually account for the activity part. For a non-ideal solution, we know the general equation still holds, right? Mu I equal to mu I naught plus RT natural log AI. So one thing about electrolytes is that even though in the equations we can easily write out, okay, once you dissolve it, you have your mu plus, you have your mu minus, you have your Z plus, you have your Z minus. When you write on paper, it sounds so clear, right? But you think about it, okay, in the real life, there's actually no way you can actually just quantify the concentration of positive species or negative species. Because they're always coexisting together. You can actually separate them. So it doesn't make any sense if you actually write everything is mu plus, mu minus. Okay, because you just cannot actually experimentally determine it. What scientists do is actually, okay, assuming today we just don't say we know the mu plus or mu minus. We actually know the mean of mu plus and mu minus. There will be actually a way that's actually more close to the reality. Okay, so how do we go from the mu plus, mu minus to the mean ionic concentration or mean ionic activity? So we define the mu is equals to the mu plus mu minus in the previous slide. If we write out the chemical potentials of your positive species and negative species separately, the total mu I of your solution is going to equals to your mu plus times your mu I plus your mu minus times your mu I minus. Then I actually expand this mu so that the first term will become mu plus times mu I plus naught plus RT natural log AI plus. So you repeat the same thing for your mu minus times mu I minus naught plus RT natural log AI minus. And then you put these terms together and the RT natural log term together. Eventually what you're going to get is actually your mu plus times your mu I plus naught plus mu minus times your mu I minus naught plus RT, you're going to have the mu plus natural log AI plus mu minus natural log AI minus. So in the end, we write this whole term as your mu plus minus naught. That represents actually the mean of the two effects. The second term will be RT natural log. I can put these things into my natural log terms. So it becomes A plus minus mu. This will be actually how you write out the chemical potentials of an electrolyte solution. So your mu I is going to equal to mu I plus minus naught plus RT natural log AI to the mu's power. So this A plus minus mu's power is actually equals to A plus to the mu plus power times A minus to the mu minus power. So we can actually take the mu's root, and you know your A plus minus will simply equals to your A plus 2 mu plus power times A minus 2 mu minus power, and take the mu's root of that. We call this mu plus minus as salt activity. We want to expand this a little bit more because we can also define my activity using my activity coefficients times the concentration. So activity equals to your activity coefficients multiply the concentration terms. So you can actually put this relationship back into these equations. So we know these things can be rewritten as A plus minus to the mu's power is going to equals to, I'm going to start from here, okay? So A plus will be your gamma plus M plus the whole thing raising to the mu plus power. And A minus will be gamma minus M minus raised to the mu minus power. Then again, we're going to put the gamma together, M together. So it will be gamma plus gamma minus mu minus. Multiply your M plus mu plus M minus mu minus. So once I have these two together, we are going to write gamma plus minus to the mu's power times M plus minus to the mu's power. So that I can rewrite my A plus minus to the mu's power equals to this. The gamma plus minus we call it as mean ionic activity coefficient. And the M, we call it as mean ionic molality. The idea is actually very simple. Idea is actually we cannot actually really define just the positive species or negative species. Okay, so what we do is actually we introduce the concept of the mean ionic molality or the mean ionic activity coefficient or the mean ionic activity, sometimes also called the salt activity. All this terminology, you just need to get familiar with it so that in the next lectures, you will know how to actually apply all these things.